The inverse of a function. We want to look at finding the inverse of a function. Let's suppose we have a function f that is given by the 3 points 1, 4, 2, 5, and 3, 6. What does it mean to find the inverse of such a function? To better understand this, let's draw a simple diagram. So here I have a set of numbers that I'm going to call the domain, and here is a set of numbers that I'm going to call the range. In this particular function, we are taking the number 1 and sending it to a new number 4. And the function f is what does that, right? So when you plug the number 1 into your function, you get the number 4 out of your function. The number 2 gets taken to the number 5. And the number 3 goes to the number 6. This is what a function does. It assigns a unique number to a given number. So what is the inverse doing? The inverse is simply reversing the order of the coordinates. So if the function f consists of the coordinates 1, 4, 2, 5, and 3, 6, its inverse, which I will temporarily call g, is just going to be the set of points 4, 1, 5, 2, and 6, 3. So what's happening here is the inverse is the function that takes the number that you got and sends it back to where it came from, right? So the number 5 goes back to the number 2, the number 6 goes back to the number 3, etc. This is what the inverse function is doing. And the notation for that inverse function is we just use the same letter as the original function, in this case f, and we put a little -1 here. And that represents the inverse of f. And usually the way we say this is we just simply say f inverse. Now, the inverse function is a function in its own right. So in other words, the domain of your inverse function, in this case, would be the numbers 4, 5, and 6. And your inverse function is taking those numbers and sending them back to the numbers 1, 2, and 3. So this set over here is the domain of f, but it is the range of f inverse. And over here, this is the range of f, but it is the domain of f inverse. So the concept of an inverse function is a very simple one, but it's also a very important one. Basically, what the inverse is just a way of undoing what the function did. So here we have an example. Let's say we have the function f of x is equal to 2x minus 3. We want to find the equation that represents the inverse of this function. So before we do that, let's just understand a couple of things about the function f. So f of x is 2x minus 3. So if I wanted to make a table of some values, some x values and y values, I can plug in some numbers for x, right? So for example, I can plug in x equals 2. That's going to give us y equals 1. If x equals 1, y will be -1. If x equals 0, y will be -3. And if x equals -1, y will be -5. So these are just a few random points. So now we know that there's going to be some inverse function, right? Maybe we don't know what that is right at the moment, but whatever that inverse function is, it is going to take these points and it's going to reverse the coordinates. So instead of 2, 1, we'll have 1, 2. And then we'll have -1, 1, -3, 0, and -5, -1. So the question is, what is the equation for this function? So let's go ahead and outline the procedure. First thing I'm going to do is take my original function, f of x equals 2x minus 3, and I'm going to replace f of x with the letter y. Okay, this makes it just a little bit easier to go ahead and do what we need to do here. Now remember, what an inverse function is doing is it's just switching x and y. So if I want the inverse of this function, what I need to do is switch x and y. So y becomes x, and x becomes y. All right, so this is the main step here. So we're just switching x and y. And now I'm just going to solve for y again. So to solve for y here, I'm going to add 3 to both sides. This gives us x plus 3 equals 2y. And then we'll go ahead and divide by 2. And this gives us x plus 3 divided by 2 is equal to y. So our inverse is this equation. It is y equals x plus 3 divided by 2. And now we're just going to rename this as f inverse of x. And this should be the equation that is the inverse of the original equation. So let's go ahead and put that in. So it's x plus 3 divided by 2. And now what you can do to make sure that we have the right answer here is you can check some of these numbers, right? So for example, when x is equal to negative 1, looking at this one right here, what do we get for f inverse of negative 1? Well, we're just going to plug negative 1 in here. So that's negative 1 plus 3 divided by 2, which is equal to 2 divided by 2, which is equal to 1. So notice that you do indeed get the number 1 here. And you can do this for the rest of the points as well. You can pause the video if you want. Plug in these x values, and you should get these y values coming out. So, as an equation, this is the inverse of the original. One final thing to point out here is the graph of the function f of x equals 2x minus 3, and the function f inverse of x equals x plus 3 divided by 2. Notice that the original function is this line right here, and the inverse function is this line right here. And if you draw the line y equals x, which is the line that comes right through the origin here at a 45-degree angle, you should notice that these two lines are mirror images of each other across this line. So anytime you graph inverses, you're always going to see the graphs are a reflection of each other across this line. So let's graph the function f of x equals x squared minus 2 and its inverse. All right, so we'll start with f of x equals x squared minus 2. Lots of different ways you could graph this. I'll just plug in some points. So let me plug in 0, 1, 2, negative 1, and negative 2. And when I plug those in, so when I plug in 2, I'm going to get 2. Plugging in 1 gives us negative 1. 0 gives us negative 2, and etc. Now, its inverse function, we don't know what that is at the moment, but whatever it is, provided that it exists, by the way, what it should do is simply reverse these points. Okay, so if we reverse the coordinates of all these points, this is what we get. So now what I'm going to do is show you what the graph of these things look like. All right, so here it is. So here is our original function, x squared minus 2. That's this parabola right here. You can verify that all of these points are on that graph. And here is our inverse right here. And that's just all of these points. And once again, you should notice that if you look across this line, you can see that we have a very clear reflection. You see how these two functions, not functions, do you see how these two graphs are mirror images of each other? Okay, now what is the equation for the inverse? So how do I do this part here? Well, remember, we have y equals x squared minus 2. That was our original. We're going to switch x and y. And then we're going to solve for y. So if I add 2 to both sides, I get this. And then if I take the square root of both sides, something really interesting happens here. I get plus or minus the square root of x plus 2 is equal to y. So y is equal to plus or minus the square root of x plus 2. What's interesting about this is actually not a function. Okay? Now, why is it not a function? Well, you can actually see it in the graph because this is the green graph here. Notice that if you draw a vertical line anywhere here, you're going to hit that graph twice. That means it's not a function. Or to put it in a different way, when you're plugging in an x value, you are getting two different y values. For example, when you plug in x equals 2, you get y equals 2. And when you plug in x equals 2, you get y equals negative 2. That's this point here and this point here. That can't happen if you actually have a function, okay? So there is no inverse function that exists here. We only have an inverse equation, which is x equals y squared minus 2. Because when you solve for y, you get this plus or minus symbol here, and that means that you're going to have two y values for one x value, and that can't happen. So we do have an inverse, but we don't have an inverse function. So now we need to talk about when do we have an inverse function and when do we not have an inverse function. So to talk about this, we need to define what it means to be a one-to-one function. So a function is one-to-one if every element in the range comes from exactly one element in the domain. So if we just consider the function y equals x squared, I'm going to ask the question, is this one-to-one? Well, look at the graph. When you plug in x equals 2, you get y equals 4. When you plug in x equals negative 2, you get y equals 4. So two different x values have the same y value. This does not happen in a one-to-one function. So no, this is not one-to-one. Or to put it more succinctly, anytime you can draw a horizontal line, if that horizontal line intersects the graph more than once, it is not a one-to-one function. So what would a one-to-one function look like? Well, for example, a function like y equals x cubed would be a one-to-one function. If you graph the function y equals x cubed, you get something like this. And I want you to notice that, first of all, every vertical line that you draw only hits the graph one time. That's necessary. But also, every horizontal line that you draw intersects the graph only one time. So this function is one-to-one. Now, why do we care about one-to-one functions? Well, because if a function is not one-to-one, for example, this function here, it means that no inverse function exists. And actually, let's just go back to the previous page here. If you take a look at these two graphs, notice that the first graph, right, this one right here, y equals x squared minus 2, is not a one-to-one function. So when you find its inverse, which basically just takes this picture and turns it on its side, now those horizontal lines that were hitting the graph 2 times, they become vertical lines that are hitting the graph 2 times. And remember, anytime a vertical line intercepts the graph more than once, you don't have a function. So if we want to have an inverse function, we have to make sure that our original function is one-to-one in the first place. So if y equals f of x is a one-to-one function, then the inverse of f is also a function and can be denoted y equals f inverse of x, right? And we've already talked about this. So if you start with a one-to-one function, your inverse will also be a function. So in this example, let's go ahead and find the inverse of the function g of x equals x minus 4 divided by x minus 2. Now, it does turn out that this function is one-to-one. I'll show you what that looks like in the end, but let's go ahead and find the inverse. So remember the process for finding an inverse. I'm going to start with my function. First step is to change g of x to y. And then the part where you find the inverse function, y becomes x and x becomes y. So both of these x's on the other side become y. Okay? Now what I need to do is take this equation and solve for y. So to solve for y, what I'm going to do here is multiply both sides by y minus 2. This is going to allow us to cancel the y minus 2 on the right-hand side. So there we just get y minus 4. And on the left-hand side, I'm going to multiply this out. This gives us x times y minus 2 times x. Okay, now keep in mind, we're trying to solve for y. Notice that we have a y here and we have a y here. So we're going to get those on the same side. I'm going to subtract y from both sides. And at the same time, let's go ahead and add 2x to both sides. So we're going to have xy minus y is equal to, right, because these cancel. And on the other side, we have negative 4 plus 2x, or 2x minus 4. Next, the reason we did this is so that we can get this y and factor it out. So we have y times x minus 1 is equal to 2x minus 4. And if we divide by x minus 1, we end up with y equals 2x minus 4 divided by x minus 1. And that is our inverse. Now, if you go back to the beginning, our function was g of x equals x minus 4 divided by x minus 2. And now we know g inverse of x, right? That's this function down here, 2x minus 4 divided by x minus 1. All right, now do we believe that these are inverses? Well, we can do a simple check, and this isn't a sure thing, but it will definitely help you understand if this is an inverse or not. So what I can do is I can plug in a value for x into my function and see what we get. So just pick a random value. Of course, one value that you cannot pick is you cannot pick x equals 2 because 2 minus 2 is 0 here in the bottom, right? So as long as we pick some other number, let's pick x equals 5. If I plug in 5, I get g of 5 is equal to 5 minus 4 divided by 5 minus 2. This is equal to 1/3. So g of 5 is equal to 1/3. Now, if this truly is the inverse, then that means if I plug the number 1/3 into this function, I should get the number 5 out of it. So let's see if that happens. So let's do g inverse of 1/3. Now, this is a little bit trickier. It's going to be 2 times 1/3 minus 4 divided by 1/3 minus 1. This is 2/3 minus 4 divided by 1/3 minus 1, right? So I just did 2 times 1/3 is 2/3. Now, to simplify this, there's a couple of different ways you can do it. I'm going to multiply the top and the bottom here by 3 because that's going to cancel out the fraction. So when I do 3 times 2/3, that's going to give us 2. And then we have 3 times negative 4, that's going to be negative 12. Divided by, in the bottom here, we have 3 times 1/3, which is going to be 1 minus, And then 3 times negative 1 is negative 3. And this is equal to negative 10 divided by negative 2, which is equal to 5. So G inverse of 1/3 is equal to 5. So do you see that? Do you see how it reversed the coordinates, right? So when I plug in 5 into the original, I get 1/3. When I plug 1/3 into the inverse, I get 5 back. Now, that doesn't prove that these are inverses, right? Like, that could happen sometimes even when they're not inverses. But the fact that it happened for a randomly chosen value means that it's very likely that we have the correct answer here for the inverse. Now, just to talk about the graphs a little bit, I don't have the graphs on the same set of axes here because if you put these on the same set of axes, it's kind of hard to see what's going on. But here is the original function, and here is the graph of that original function. It's a rational function. Notice that it has a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 1. And here is the graph of the inverse function that we found here. It is also a rational function. Notice that the horizontal asymptote is y equals 2 and the vertical asymptote is x equals 1. So what I want to point out is since an inverse switches the x's and y's, it also switches the horizontal and vertical asymptotes. So the horizontal asymptote, y equals 1, became the vertical asymptote, x equals 1. And the vertical asymptote here, x equals 2, became the horizontal asymptote, y equals 2. Next, let's graph the function y equals 2 to the x and its inverse, x equals 2 to the y. So let's just recall that if y equals 2 to the x, we can graph this by getting some points. So for example, if x equals 3, y is going to be 2 to the third, which is 8. If x equals 2, 2 squared is 4. X equals 1, 2 to the 1 is 2. 0 gives us 1. Negative 1 is going to give us 1/2, and negative 2 will give us 1/4. So if I graph the inverse, which is x equals 2 to the y, so all I did here is I just switched x and y, I know that this is just going to switch the coordinates of these points. Now, we will talk about how to solve for y here. Right? Not right now, but eventually in the next section, we'll talk about how you solve for y there. But this is the table of values that you would get for the inverse. So bringing these in now, notice that the graph of y equals 2 to the x is this graph right here. Right? So that's our basic exponential graph. And if you graph all of these points, you will get this graph, which once again is a mirror image across this line, y equals x. Right? So you can see that you have a mirror image here. This graph here is really special. It's going to turn out that this graph is what we call a logarithm. And that really is the whole point of this chapter. That's why we talk about inverse functions, because the inverse of an exponential function is what we call a logarithmic function. So again, we'll be defining this in the next video, but I just wanted to give you a little sneak peek in this section. So as a summary here on functions, relations, and inverses, every function is a relation, but not every relation is a function, okay? Every function has an inverse, but only one-to-one functions have inverses that are also functions. The domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. If y equals f of x is a one-to-one function, then we can use the notation y equals f inverse of x to represent its inverse function. The graph of a function and its inverse have symmetry about the line y equals x. And finally, if the point AB belongs to the function f, then the point BA belongs to the inverse of that function f. And that concludes this video lesson.